We're going to be taking a look at rates of change. Um, this is the real fundamentals to what will become calculus at the start of next semester. So if you can get your head around this, you'll be in a good place ready for calculus. 6.1 average rate of change. So firstly, we need to identify rates. So here's the first rate. We've got the speed of a car. So the speed of the car is 70 kilometers per hour. Notice that there are two quantities involved in this. So we've got a change in kilometers and we've got a change in hours. So the car covers a distance of 70 k's every hour that we are in the car. Cost of fuel, $1.39 per litre. So petrol will cost us $1.39 for every litre that we put into it. Gradient of the road is 1 to 25. So the road will rise by 1 unit up for every 25 units that we go across it horizontally. So rate of change, we're looking at the change of one quantity over the change of another. And here I'm referring to them as quantities A and B. So the rate of change of A with respect to B, the amount of A per B. So it's a change in A over the change in B. Problem 1, we need to identify which ones are rates and which ones are not. So remember, we're looking at the change in two quantities. So 20 meters per second, two quantities, meters and seconds. So therefore, that is a rate. 75 cents per packet. So per packet, we are charged 75 cents, two quantities again. And here we just have an amount, $13. There's no change there with respect to another quantity. So it's got the one quantity. So therefore, it is not a rate. Let's look at this problem. Shane travelled to Melbourne from Wodonga in 2 hours and 45 minutes. The distance between Wodonga and Melbourne is 321 kilometres. Express this as a rate in kilometres per hour. So my speed, which is the rate, is the distance, 321, over the amount of time, which is 2.75 hours, to give me a rate of 116.727 kilometres per hour. So that's the rate at which I am travelling. It's the speed. And of course, how did I go from 2 hours and 45 minutes to 2.75? It's shown here. You guys understand that 45 minutes is 3/4 of an hour, so it becomes quite easy. But sometimes you might be given something like 2 hours and 16 minutes. How do you go and convert that to hours? You follow the same process here. Let's take a look at constant rates. So these are rates which are not changing, so it remains the same throughout it. And it's shown typically here as a straight line graph. In this example, what we see is that there's a rate for fuel of $1.60 per litre. So that tells us that if we purchase 1 litre, it will cost us $1.60. If we purchase 10 litres, it would cost us $16. If we purchased 100 litres, it will cost us $160. Notice that the gradient, the steepness of this line here, is equal to the rate. So if we calculate the gradient, then you'll see that we get that $1.60 per litre. So there's the dollars, there's the litres, and it's $1.60 per litre. So the rate is equal to the gradient. So the rate is equal to the gradient, which is rise on run. We look at that as being the change in the y quantity over the change in the x quantity. And we sometimes write it like this, delta y over delta x. So it's that little triangle which is in the Greek alphabet representing delta, just means change. You'll see that a lot. Here we have a positive rate, it's increasing, a negative rate, it's decreasing, and then the steepness of the line tells us if one is faster than another. So here you can see that we have a flatter line or a lower line here. Okay, it's not as steep. That represents a slower rate in comparison to this steeper line, which is a faster rate. Problem 1, the graph shown represents the height in meters of a hot air balloon as time goes by in hours after it's launched from a mountaintop. Use the graph to firstly find the gradient. So as you know, 2 points, so we've got 0, 500, we've got 5, 1100 here. So to work out the gradient, m, it's y2 take y1 over x2 take x1. We do that calculation, we get 120. So the gradient there is just 120. I don't put in the units here, okay? So just write the number 120. That's the gradient. B, what's the rate of change? Well, it's the gradient, but we now include the quantity. Yeah, we include the quantities. So we've got 120, and what we've got there is meters per hour. So we are rising in that hot air balloon at a rate of 120 meters for every hour that goes by. Then we need to find the equation. So of course the equation for this, we're going to have h for height is going to equal the gradient, 120 times the time that goes by, plus the vertical intercept, so that 500 there. And this makes sense because if time was 0, then the height would be 500. So in other words, the mountaintop is 500 meters above sea level. That's where we've begun from. Problem 2. The length of a spring, we're referring to that as being capital L, increases to varying degrees when different forces, and they're measured in newtons, are applied. Okay, so here we have forces applied, and these are the lengths. So we've got 0, 15 as one point, 20, 55 as another. Find the equation that relates the length of the spring to the force applied. You can see here that we're going up by a constant amount, so it's a linear. All right, so as we jump by 5 in the force, the length of the spring increases by 10 meters. You can see that each time. So it's going up by a constant amount. All right, so to work out the equation, vertical intercept 0, 15. The gradient is going to equal from the 2 points, so y2 take y1 over x2 take x1, and gives us a gradient of 2. And so the length is going to equal 2 times the force applied plus 15, where 15 is that vertical intercept at the beginning. So what's our rate here? Our rate is 2 meters for every newton that is applied to the spring. Sometimes we don't have, and quite often in fact, we don't have constant rates. We have what we refer to as variable rates. So the rates are changing as the vertical axis changes. Let's consider this problem here. All right, so we've got one quantity changing with another, and this is the graph that's shown. Firstly, we need to work out the rate of change, whether it's constant or variable. All right, so if it's straight, it's going to be constant. So we're going to break it up from A to B, and you can see there that that's a curve. So that represents a variable rate. As the X changes, the Y changes, of course, but it doesn't do it consistently. You can see that shape there, it's a curve, so therefore that represents a variable rate. From B to C, it's a straight line, so that represents a constant rate, and C to D, also a straight line, represents the constant rate. Now what we have to do is recognize for part B here whether it's positive, negative, or 0. So from A to B, as X gets larger, Y is getting larger. It's not doing it consistently, but it is getting larger. This represents a positive rate because it's going up towards the right. From B to C, we have a horizontal line. So as X increases, Y does not change. That represents a 0 rate. And as we move from C to D, we're moving at a consistent rate. So as X gets larger, Y is getting smaller, and it does so consistently. But because it's getting smaller, the graph goes down towards the right. That represents a negative rate. So when we're dealing with variable rates, sometimes we want to calculate the average rate. I'm going to give you an example here of a fly and its velocity. So just being technical, it's probably a big application of physics here, but the velocity of an object is equal to the change in displacement over change in time. For simplicity, just think of velocity as being speed and displacement as being distance. So speed is equal to the change in distance over the change in time. But to be technical, it's actually velocity is equal to the change in displacement over change in time. The displacement of a fly is given by the function d of t equaling t squared plus 3. So this is the rule that gives us the displacement of the fly for any amount of time. Here's a graph showing the displacement of the fly. So we've got displacement on this axis and time over here. And you can see we've got our parabola. Remember, it was t squared plus 3. So that's shown here. What we are interested in is calculating the average the average velocity of the fly between the 1 second mark and 4 second marks. So that average velocity is in fact an average rate, and it's the rate of the change in displacement over the change in time. So the average velocity is going to equal the gradient of the line that joins these 2 points. That is when time is 1 second and time is 4 seconds. If I substitute 1 into the displacement function, 1 squared plus 3, I'll get the 4. And if I substitute 4 into the displacement function, 4 squared plus 3, I'll get that 19. So I've got 2 points. Remembering that the average velocity means that we're talking about the average rate of change of displacement with respect to time. So it's simply going to be equal to the gradient that joins these 2 points. Sorry, the gradient of the line that joins these 2 points. Technically, we often refer to that line as being a chord. So what we have to do is just calculate the gradient of this straight line. So putting it all together, the fly's average velocity will equal the fly's average rate of change. So that's the change in displacement over change in time. I refer to that as being delta D over delta T. My rise on run, so D2 take D1 over T2 take T1. My calculation, and I end up with 5 meters per second. So bringing that back to the graph. On average, for every second that goes past, the fly will achieve a displacement of 5 meters. So that average rate of change is 5 meters per second. Obviously, that's not a constant rate because we can see this changing here. All right, it's only an average rate of change. So it takes into account that this here will be a bit slower than 5 meters per second. This here will be a bit quicker than 5 meters per second. But overall, the average will be 5 meters per second. So average rate of change is the change in y over change of x as represented here. Here we have a scenario. Calculate the average rate of change between the points P and Q. So here's P, here's Q. As time goes by, you can see the value of the distance. The distance is actually increasing, so we should see a positive rate. You can see that this is the curve that we're dealing with between P and Q. So it's not a constant rate, but we can calculate the average rate. And the average rate of change is going to equal the gradient of this blue chord here. Firstly, what we have to do is realize that point P is the position 2, 30, and point Q has the position 7, 48. So the average rate of change in displacement over change in time, 48 take 30 over 7 take 2 to give us 18 on 5 meters per second. Once again, going back to the graph, you can see, if we're considering the steepness of this curve, here the displacement is fairly quick, all right, because it's fairly steep. Over here, it's starting to flatten out a little bit, that represents a slower velocity. All right, so we've got distance, time, and where it's steep, that will represent a faster rate, that is a faster velocity. And here you can see where it's starting to flatten out, that represents a slower velocity.